This conference will now be recorded.
Hello, everyone, and thank you for attending this evening. My name is Anna Vanscoik, and I work at the Hopewell branch for the Mercer County Library System. Before we get started tonight, I wanted to share a couple other programs that are coming up virtually. So it'll be in the similar format where you can attend from the comfort of your home or your porch or the beach or wherever you may be. The first one is on Thursday, July 21st, and that's at 6:30 in the evening. We'll be having the mystery of the coral reefs, and we'll be having a presenter from the Aquarian Divers for Coral Society who will be sharing the secrets of the coral reef and its importance to the ecosystem, etc. And again, that's Thursday, July 21st at 6:30 in the evening, and you can register for that to receive the link on our website, mcl.org, or if you've downloaded our app, My MCLSNJ, you can register that way as well. Going along with our theme, we have a shark attack program on Friday, July 29th at 2 in the afternoon. And that is going to be presented by the Center of Aquatic Sciences at Adventure Aquarium. And again, that is a virtual program. And you're going to notice we have a little bit of a theme with tonight's program, as well as the coral reef and the sharks. The summer reading program's theme is Oceans of Possibilities. And I do encourage you to register for the summer reading program. And I've put the link into the chat there, so you can visit that after the program and register for at your local branch. You're able to do it through the online access, and you can register your reading and win prizes. So let's get on to this evening. Tonight we have the Arctic Meltdown. What did it, why, and why it matters to all of us. Jennifer Francis will be speaking for us this evening. She is the acting deputy director and a senior scientist at the Woodwell Climate Research Center in Falmouth, Massachusetts. Previously, she spent 24 years as a research professor in the Department of Marine and Coastal Sciences at Rutgers University, where she studied the Arctic climate system and how rapid Arctic change is affecting areas beyond the Arctic, particularly extreme weather in the Northern Hemisphere. Jennifer earned a BS in meteorology at San Jose State University in 1988 and a PhD in atmospheric sciences from the University of Washington in 1994. She and her husband circumnavigated the globe by sail during the 1980s, including the Arctic, which is where her interest in the region began. Dr. Francis, thank you so much. I'm going to pass it over to you.
Great. Thank you so much, Anna and Laura. Thank you for inviting me to be here tonight. It's a real honor to be with all of your library members and everyone else who's here. Thank you for taking time out of your summer on this beautiful evening. And I'm going to go ahead and share my screen so we can get rolling. And hopefully this will all look good. Okay. All right, so as the title suggests, we're going to be talking about the Arctic quite a bit, and you've probably heard that things are changing up there really fast. We're losing ice at a very disturbing rate, but that might seem like a very far away place to New Jersey. Why would anybody care that the ice is disappearing up there? Well, that's what we're going to find out about today. And even more broadly, we're going to talk about climate change more generally and how that's affecting our weather patterns. And I want to start out by going back not very far in time, just about a year ago, when we had it was an unprecedented heat wave that hit the Pacific Northwest part of North America. And what you're seeing in this map on the right here are colors that are showing you how different the temperatures were during this heat wave compared to normal. So these red colors here are much above normal. These are degrees Celsius, which are not quite twice as big as degrees Fahrenheit. And you can see this big blob of red parked right over the Pacific Northwest. This was indeed an unprecedented heat wave. And in fact, research since this occurred last year has determined that not only did climate change play a role in making it bad, but it would have been impossible without climate change. This is actually a pretty new result that has come out recently. So this was a very big deal, and it's in a place where they're not used to having a lot of heat. People in this part of the world don't have air conditioners generally because it's usually not very hot. But I want you to notice a couple other things. So down here over the southwest part of the United States, these colors are telling us that it was actually quite a bit colder than normal. And then over here in New England, where we are, it was also warmer than normal. So you see these differences in temperature that are all connected together. When you have an extreme of one type in one place, almost always you have maybe not an extreme, but a difference from normal of the opposite flavor right next door. So this is something I want you to remember. When you get an extreme of one sort, it's never in isolation. There's always unusual things happening next door. So why did this happen? Well, this map here is showing you how the jet stream looked during this heat wave. The jet stream is a river of fast-moving winds high up in the atmosphere where jets tend to fly. And when it's in one of these very convoluted patterns, like it's showing here, you can follow the words jet stream, you can see that it's taking this big loop way up to the north. And when it does that, the winds that are generally blowing from the west are bringing tropical air all the way up into Alaska. So that is really what created this big bulge of hot air. The jet stream generally separates the cold air to the north up in the Arctic from the much warmer air to the south in the tropics. And when it bulges like this, it allows that warm air from the tropics to penetrate much farther north than normal. But you remember that cold area down in the southwest? Well, the jet stream's responsible for that too. When it takes a big dip southward like this, that cold air from the Arctic can penetrate much farther south than it normally would. And that is what caused that cool spot that I showed you on the map before. So another very extreme event that happened recently. So this is about 1.5 years ago now. You'll probably remember the Texas freeze. It was all over the headlines. Very, very cold air, extremely cold air penetrated all the way down to the border with Mexico in February of 2021. This caused a lot of problems for people living in the southern regions of Texas and Oklahoma and Arkansas, because again, these temperatures were much, much colder than they're used to. And in fact, in Dallas, during one of the days of this cold spell, it was below zero. It was colder in Dallas than it was in much of Greenland and much of Alaska during this period. So this was super unusual, not only in the extreme temperatures, but the fact that it dipped so far south, and it also lasted a really long time and covered a huge section of North America. This was another unprecedented event. This time it was cold. And again, we can look to the jet stream for the reason why this happened. So now the jet stream is being shown as these words that say storm track. So instead of bulging northward like we saw for the heat wave, we're seeing it dip way south. And that's allowing that cold air from the north to penetrate all the way down into southern Texas. But you also see something else going on here. We have this pink circle here labeled polar vortex. And you've heard that term. It's been all over the media. And I would say that in many cases, it's not being used correctly. So one thing you're going to learn tonight is what the polar vortex really is and why it matters. And even we think it's changing and why it's changing. So here's a schematic of the jet stream, which is being shown in the light blue here. We can see we're looking down over the Atlantic Ocean with the USA on the left. And on top of that is a darker blue circle, and this is the polar vortex. So as I mentioned, the jet stream exists up high in the atmosphere at a height roughly where jets fly. And the polar vortex, however, is much, much higher. It's between 10 and 30 miles above the surface. It's much smaller generally. It sits right over the North Pole, and it's only there in the wintertime, whereas the jet stream is there all the time. So most of the time, the polar vortex sits up there and it kind of spins around. It has very, very cold air inside the middle of it with very strong winds circling it from west to east. And usually it stays up there. It really doesn't bother anybody. It doesn't affect our weather. But every once in a while, the polar vortex becomes disrupted. And by disrupted, I mean it can stretch into sort of a bean shape, or it can even split into two parts. And this is what's being depicted here. When this happens, those pools of cold air in those split vortex areas can drift southward down over the continents. And in fact, this is exactly what happened during that Texas cold freeze that I was just talking about. And when that happens, it brings all that really cold air southward with it. It makes the jet stream take on this very wavy pattern, and that both of those things together reinforce that cold air penetrating way far south. And we can even look at what it looks like when the stratospheric polar vortex is disrupted. This is actual data produced by this fellow Simon Clark, and showing how the polar vortex can sometimes split. So you can see how it starts out quite circular, then it starts to stretch apart, and then it splits up into these two pieces. So this is what one of those disrupted split polar vortexes looks like. And going back to what the temperatures were doing on that during that cold freeze in Texas, we can see again these blue colors over North America, suggesting it's much, much colder than normal. And we also see some very cold temperatures also over Siberia. And you remember I said those two pieces of the polar vortex split and then went down over the continent. So it wasn't just North America that was experiencing extreme cold. And I also want you to notice what I was saying before about when you have an extreme of one sort being next to an extreme of the opposite sort right next door. So you can see that these red colors over northeastern Canada are telling us it's much warmer than normal, and also over much of China. And in the Arctic, this far northern area that's bright red here is telling us that it's much warmer than normal because the polar vortex split apart and it took all the cold air with it. So the Arctic ends up being warm when we have these disruptions in the stratospheric polar vortex. So these extreme events like that heat wave I talked about and like this cold spell in February 2021 are just two types of extreme events. And what we're noticing is that extreme weather events are increasing over time. And that's what this graph is showing you. It's showing some what they're calling mega disasters. So extreme events that caused more than $20 billion in damage. And you can see starting back in 1980, we're seeing a general increase in the frequency of these mega disasters. Of course, part of the cost of these disasters is the fact that coastal areas and vulnerable areas have more people in them. They have more infrastructure in them. So some of that cost is due to that. But we also know that extreme weather events more generally are increasing in frequency. So it's not just the cost of the damage that's being done, but we also know that extreme weather events have roughly tripled since 1980 worldwide. Okay, so I'm going to take a step back now and look at how the Earth's temperature has changed over the last 20,000 years. And that's what this line on this graph is showing us. It's how the temperature of the Earth has differed from what it was, let's say, in the 1950s, roughly. So back 20,000 years ago, of course, this was when we had our last ice age, and the Earth was a little over 3 degrees colder than it is, or say, a century ago. And we came out of that ice age, the Earth warmed up, and we got to what we call an interglacial, which is a relatively warm period for the Earth. And this variability, this change in the Earth's temperature, we know was caused by natural fluctuations. So things like shifts in the Earth's orbit around the sun, shifts in the tilt of the Earth relative to the sun. These are all the kinds of things that can cause these changes in the Earth's temperatures over thousands of years. But of course, we know that what's happening now is not natural causes. In fact, I want you to notice that if there were only natural causes occurring right now, the Earth would be in a cooling phase. But instead, we're in a rapid warming phase. And this is because of all of the greenhouse gases, the heat trapping gases that we've been dumping into the atmosphere since the 1900s. And so here we are now, a little over a degree Celsius warmer than we were before we started changing the atmosphere so dramatically. And if we keep going this way, by the end of the century, which sounds like a long time away, but here we are in 2022, so this is 80 years from now. Some of you might have grandchildren that will be alive then. This is where we're headed, something like 2 to 3 degrees warmer than the last century. And I also want you to notice that the difference in temperature of the Earth between an ice age and an interglacial is only 3 degrees. It doesn't take much warming to drastically change what the Earth's climate is like. And here we are already having changed it 1 degree, and we're expecting another 2 degrees or so to happen in the next 80 years. So, it may not sound like much that the Earth has warmed a degree and a bit, but it is a lot when you look back in time and see how different the Earth was with only a 3 degree change in temperature. So talking still about temperature here, but now how it's changing across the world differently in some places relative to other places. This is a plot that you probably have not seen before. It's a little different from many that you usually see where it just shows the changes in temperature or the trends in temperature. This is showing us how the temperature has changed in one place relative to the globe as a whole. So the places that are blue mean that they have warmed slower than the globe as a whole, and the red or pink places are warming faster than the globe as a whole. And so what you notice right away is that the land areas are warming faster than the globe as a whole and much faster than the oceans are warming. And the Arctic is warming the fastest of all. These deep red colors are telling us that the Arctic is warming much, much faster than the globe as a whole. In fact, that number is something like 3, closing in on 4 times faster warming than the globe as a whole. It's a really big deal. And along with that warming in the Arctic, we know the sea ice there is disappearing really fast. And what this animation is showing us as we look down on the North Pole here, there's Greenland, there's Scandinavia, there's Alaska on the bottom left here. These colors are showing us the thickness of the ice that's floating on the Arctic Ocean. And the animation takes us back to 1980 or so and brings us up to nearly the present day. And so what we're seeing here is a change from in the 80s, where the Arctic Ocean was dominated by these pinks and yellow colors, which tell us that the ice was very thick. And then as we get to near the present day, those thick ice areas are practically gone. And in fact, the ice thickness has decreased roughly 40% just in the last 40 years. It's a really fast change. And we know that because the Arctic is changing very fast, and as I said, it might seem like a very far away place, and what does it matter to you? Well, it turns out it has a big impact on all of us. So not only is the ice getting thinner, as I just showed you, but we can look at what the ice looked like back in September of 1979. This is what the Arctic Ocean typically looked like. It was mostly filled with thick ice. And then as we fast forward here to 2012, which was the summer when the sea ice was at its record minimum extent ever recorded, we can see that the white is now being replaced by these yellows and oranges. This yellow and orange area is where there used to be ice, and now there is no ice. And the big deal of that is that, of course, ice is very white, it's very reflective, and so when the sun's rays hit it, most of that energy gets reflected right back to outer space. It never enters the climate system at all. But now that we've lost so much of that bright white surface, we are absorbing much more of the sun's energy into the Arctic Ocean. And this sets up what we call a vicious cycle or a positive feedback loop. So the idea here is that as we lose some ice, it exposes more of that dark ocean, it absorbs more heat, it warms up the water, which melts more ice, and it sets up this vicious cycle. And that's one of the main reasons why the Arctic is warming so much faster than anywhere else, is because of this loss of not only the sea ice, but also the spring snow cover on the land areas. It's disappearing almost as fast as the ice has. And literally, we've lost half of the summer sea ice in the last 40 years. And if we multiply that area loss by the thickness that I showed you just before, we find that the volume of the ice has declined about 75%. We've lost 3/4 of the sea ice floating on the Arctic Ocean in less than 40 years. And this means that the Arctic surface is darker now, which means that the global surface is darker now. And the impact of that is to increase global warming by 25 to 40%, just because of losing the sea ice and the snow cover. So it's making global warming much worse than if we didn't have this ice and snow on our Arctic surface. This extra warming in the Arctic is melting the Greenland ice sheet much faster. We're seeing an acceleration of the melt of the Greenland ice sheet. That's a big deal because when that ice there melts, it flows, it puts water into the ocean, and that extra water in the ocean is now the single biggest contributor to sea level rise. So that's one way the Arctic is affecting you. It's causing, perhaps you have a home or you vacation on the Jersey Shore. That sea level rise is eroding the beaches, and it's damaging infrastructure. It's having a big role in the coastal regions. It's also accelerating the thaw of permafrost. That extra warming in the Arctic is causing permafrost, which is the soils of the high Arctic contain a lot of ice. Some of those soils have been frozen for 20,000 years. And that's a big deal because that soil contains a lot of dead plants and dead bugs and dead animals. And when that permafrost thaws, all of that stuff starts to decompose. And when it starts to decompose, it releases greenhouse gases, methane and carbon dioxide into the atmosphere. And guess what? That sets up another vicious cycle. So we heat the Arctic, we thaw more permafrost, it releases more methane and carbon dioxide into the air, which traps even more heat globally, and that accelerates the warming of the globe and the Arctic. And we're going to talk about the weather and how the rapid changes in the Arctic are affecting the jet stream winds, which, as I talked about in the beginning, the jet stream has a lot to do with those extreme events that we've been experiencing. So anything that messes with the jet stream is going to affect our weather. And let's talk about how the jet stream, or why the jet stream is there, and how the Arctic warming is affecting that jet stream. So if you can imagine a layer of air that extends from where you are in New Jersey up to the Arctic, we know that air expands when it's warm. And so this layer of air is going to be taller or thicker where it's warmer. So it's going to be thicker over New Jersey than it is over the Arctic. So if you were sitting on top of this layer and looking towards the north, it would look like you were looking down a hill, and in fact you would be. And this air that sits on top of this layer wants to flow down that hill in the atmosphere, just like water wants to flow down the side of a mountain. So this creates a wind from south to north. But because the Earth is spinning, everything in the northern hemisphere that moves gets turned to the right. And so this creates the west to east winds that we call the jet stream. It's because of this temperature difference and also the spinning of the Earth. So that's why the jet stream's there. But now think back to the Arctic warming faster, much faster than everywhere else. What's happening to the thickness of this layer? It's increasing much faster in the Arctic than it is over New Jersey. And so it's making the slope of that hill much less steep. So there's less force driving the winds from south to north, and that results in the jet stream becoming weaker. And we know that when the jet stream is weak, it tends to take these bigger south to north to south swings as it crosses, say, the North America. And what does that look like? It looks like the big waves that I showed you that were associated with those extreme events. So when we get a very wavy jet stream like this, we tend to see some very unusual weather occurring. And those big waves in the jet stream also tend to move very slowly from west to east. So that weather that they cause tends to change very slowly. It tends to be very persistent. And you can think about the heat wave that's happening out west right now. It's been there for weeks. And there's other reasons why we care about these waves in the jet stream. They actually make our weather. So you know already that the jet stream separates the cold air to the north from the warm air to the south, but the actual waves themselves create what we see on TV weather maps. So in this part of the wave where the winds are coming from the northwest is where we tend to find high pressure. It tends to be blue skies, dry conditions in this part of the wave. But in this other part of the wave over here, over New England, which is where the winds are coming from the southwest, this is where we tend to get our stormy conditions. So you might, if you're interested in weather, you might know that this is the pattern that you would see in the jet stream when we get our big coastal storms in the wintertime. This is why. This is the part of the wave in the jet stream that creates those upward motions that creates storminess. And unfortunately, though, the real jet stream is much more complicated than that nice, simple schematic I just showed you. These are what the real winds look like up high in the atmosphere. This is about a 2 to 3 week period. These red and yellow colors are showing you where the winds are the strongest. And you can see very clearly there are places, it looks like a river of wind circling the northern hemisphere, but it's very messy. There are big swirls, there are waves, it changes, it undulates, and you can imagine that it's very difficult to try to measure whether the jet stream is changing in some way or not. But you can also see that when these waves get big, like if they are right now, that wave tends to stay in place for a long time as compared to when the waves are small. So that is part of the story here. When those waves get big, we tend to see these very persistent weather patterns associated with those big waves that can lead to all sorts of extreme weather events. So I want to get back to sea ice now again. So up in the Arctic, as I mentioned, the Arctic Ocean is covered by this floating ice that's disappearing. And this graph is showing us how the area of the sea ice has been changing over the past up till this point in time, which is roughly today, and also going into the future. So this solid black line here are actual measurements of what's been happening to the extent or the area of the summer sea ice on the Arctic Ocean. We can see very clearly that it has been in a very steep decline starting around the mid-1990s or so. This gray stuff here are simulations by what we call climate models. They're these very complicated computer programs that simulate all of the processes that happen in the climate system. They simulate weather and water vapor and precipitation and ocean currents and even vegetation and some aspects of the deep ocean. And so what you can see is that these climate models are doing a really good job of capturing the changes that have happened in the sea ice, especially in the last few decades where we've seen this big decline. But what's interesting is to look into the future. And here we have what we call different scenarios for what might happen. And they largely depend on us. So we've got the red line here, which I call the do nothing line. This is if we continue to behave the way we've been behaving, burning fossil fuels, cutting down forests, putting lots of greenhouse gases into the atmosphere. If we stay on this red do nothing line, then probably sometime before the middle of this century, sometime before 2050, we're going to see all of the sea ice in the summer disappear in the Arctic. This is almost a given that we're going to see this happen. It's really a question of how fast, but it might not happen, because if we can stay on this green line here, this green line is another scenario in which we're able to drastically cut the amount of greenhouse gases that we put into the atmosphere. If we're able to take more greenhouse gases out of the atmosphere and basically do everything we can to stop the increase of greenhouse gases that are in the atmosphere, we can stay on this green line. There's still hope for that, in which case we would preserve some of the summer sea ice. So what's that going to take? Well, as I alluded to, there are really two parts to that story. We've got to emit less of these heat trapping gases, and we also have to preserve and increase the aspects of the climate system that actually remove greenhouse gases from the atmosphere. So to think about this, it's helpful to sort of compare it to a bathtub filled with water. And this water is representing how much greenhouse gases there are in the atmosphere, say right now. And of course, your bathtub has a faucet that puts water in, and it has a drain that lets the water out. Well, right now, the water that's flowing into the bathtub is much, much faster than the drain can remove from the bathtub. So to make these two things equal is what we have to do to maintain a steady level of greenhouse gases in the atmosphere. And that is how we can eventually stay on that green curve or something like it. And that involves making sure this drain doesn't get any smaller. There are ways that we can even make the drain bigger, but mainly we have to stop putting the greenhouse gases into the atmosphere and make that faucet put out less of those carbon-containing gases. So where do they come from? Well, you know, they come from burning fossil fuels. They come from our transportation system. And if we look at the ratios or the amounts of these different greenhouse gases, we see that carbon dioxide is the big player here, coming mostly from burning fossil fuels and from various industrial processes, but it also comes from cutting down forests and agricultural aspects too. Methane has been in the news a lot lately. It comes from biological processes like massive farming, a lot of animal husbandry, feeding cows grain so that they produce a lot of methane, but also from the way that we extract fossil fuels from the ground. And nitrous oxide is another greenhouse gas, mostly comes from fertilizers. And the different parts of our society where these come from, you can see the big players are generating electricity and heating our homes and businesses, from agriculture and cutting down forests, from industry, and from transportation. Those are the main places where these heat trapping gases are coming from. So that's the faucet side of things. And there are also these ways that the climate system naturally removes these greenhouse gases from the atmosphere. Of course, trees are very important in this role. So when we deforest, we're not only removing this ability to take, say, carbon dioxide out of the atmosphere, but each of these trees stores a lot of carbon in its trunk and its branches and its roots. And when you cut down a tree, that carbon ends up back in the atmosphere. So deforestation is a big thing that we really need to stop. As I mentioned, growing cattle for both dairy and beef is another source, but we are able to feed them different food, which causes them to produce much less methane. There are different kinds of plants we can grow, but we can also add things like seaweed to their food, and that reduces the amount of methane they produce. Other natural ways to reduce greenhouse gases is by wetlands, like mangroves are a huge storer of carbon. Our wetlands, our coastal marshes are also another major storage. So these are all the parts of the climate system that we need to preserve and replace if we can. And those are all big asks, but there's a lot that each of us can do, you and I. And those include our personal choices that we make every day in our lives, the kind of transportation we choose, what kind of car we buy, whether we choose to use mass transit. We can do a lot to make our homes more efficient, so we use less electricity, and every electron of electricity that we don't use, we actually save several electrons, because it takes a lot of energy to get that electricity to your wall socket. We can choose different appliances that are much more efficient. We can run our dishwashers when they're full. We can use less hot water. And as I mentioned, conservation is really the cheapest form of really mitigating this greenhouse gas emission. We can look to our community governments, and some of this involves getting ready for the changes that we know are inevitable. Sorry, I got a little tickle in my throat. I need a drink of water. So assessing the properties and infrastructure in our communities that are vulnerable to, say, sea level rise, to river flooding, to all kinds of extreme weather situations. We can plan proactively. We can mitigate those extreme impacts before they happen. We can support our towns switching from fossil fuels to more renewable energy sources, wind and solar. Again, conservation comes into play here. Our municipal buildings, we can make them more efficient. And you need to get involved. You know, it's amazing how one person can have a huge impact on a community. So getting involved in committees in your towns, and you know, even you can run for office, for the planning board, for the select board, for conservation commission. All of those have a big role to play in making our municipal governments doing the right thing to move us in the right direction. And then there's the national and state level, of course, and the main thing that each of us can do there is to vote for leaders who get this problem, they get the crisis that we're facing, how important it is, and they also understand the various ways that we can keep us on that green curve. One of the quickest and most substantial ways we could do that is to stop subsidizing fossil fuel industries, the exploration, the distribution, and the production of it. This all, I mean, just in the United States alone, we subsidize the fossil fuel industry approximately $600 billion a year. And you know that they're making record profits right now while gas prices are so high. They don't need these subsidies. And that money could be used for a lot of other things, including incentivizing renewable energy sources, increasing our education, and adapting our communities to the extreme weather that we know is going to continue to increase, at least for a while, unless we can get ourselves on that green curve. And finally, I don't think I have to tell you this because you're here. You're educating yourself. But what you need to do now is go home, go to your workplaces, and talk about this. Make people understand, or help people understand, that we are in a crisis, but there are things that we can do. There's a lot we can do. And whenever there's an extreme weather event, you can help people understand why it happened. Look at the jet stream that was occurring during that extreme event. We were just talking before we got started with this about how it's been relatively cool in the Northeast this summer so far, while the middle of the country has been baking. Well, you can probably picture what the jet stream looks like to cause that. We've had a big bulge northward in the jet stream over the middle of the country and a southward dip over New England. And that's why we've been relatively cool while the center and the west have been baking this summer. It's all connected. So just to leave you with a kind of a cool quote, I think, is, you know, what we're really trying to do here is avoid the unmanageable, which means we want to keep us on that green curve, not take the do nothing curve. And we want to manage the unavoidable. So this is talking about, we know that we're going to continue to have extreme weather increasing for a while at least. We're going to continue to lose sea ice. We're going to continue to see the Arctic warm up. And some of this we just cannot avoid. So that's what we need to prepare for. But there's a lot we can do to minimize or to reduce anyway the impacts of these extreme events that we know are coming our way. So these are the two sort of sides of the coin, and both of those are completely doable to some extent. We can make it much less bad for the future than it could be otherwise. So with that, I will thank you so much again for inviting me, and I look forward to some of your questions.
Dr. Francis, thank you so much for such an informative talk. I mean, it's all things that I hear in the media, and I just have to let you know that your graphics and your explanations, I'm like, oh, I get it. I
I'm
understand
so
the jet
glad.
stream. I understand the jet stream. And I love the bathtub. Well, I don't love that we have the bathtub
I know.
analogy, but I think the analogy really explains it very, very
Mhm,
well.
mhm,
And I think as someone who has children, as me, I have children, and I constantly worry about what's going to be happening in the future. So I just wanted to thank you for that before I let other people ask questions, especially how you do point out things that we can do,
mhm.
because it's a big topic, and I think sometimes it's so overwhelming. So I do
Yes,
appreciate that at the end. And
thank
one of
you.
the things, one of the comments, and I think you addressed this, but it talks about, are the North Atlantic waters colder due to the ice melt? And that's not true because of what you were talking about, how the sun is being absorbed now, the earth is absorbing the heat. Is that correct?
So I think that question might actually be with respect to that blue blob that I didn't talk about, but it was in the North Atlantic, so not in the Arctic. It's actually south of Greenland. If you remember that map that I showed of how the temperatures are changing relative to the globe as a whole,
Mhm.
there was a big blue bullseye in the North Atlantic Ocean. And that is a really interesting phenomenon that's getting a lot of attention right now by the research community. And in fact, it is caused by extra fresh water coming off of the Greenland ice sheet with the extra melting that's happening there, in addition to extra river runoff flowing into the Arctic Ocean, and then it flows out into the North Atlantic. So this extra fresh water is more buoyant. It floats on top of the salt water. And because that fresh water is there, it's preventing the mixing of the ocean waters down to the deeper levels and bringing up the warmer water that's just underneath that fresh water. And so it shows up as this blob of colder water. And it has a lot of implications actually for weather, especially in Western Europe, because just like the Arctic warming relative to the areas farther south is changing the slope of the hill in the atmosphere, so is the presence of that cold blue blob in the North Atlantic. So it's actually helping to strengthen the jet stream south of it because it's making the hill steeper to its south. And that is sending more storms, especially in the winter, into the UK and Western Europe. So it's all very interesting and getting a lot of research attention right now. So I think that's what that question was about.
Thank you so much. And then I do want to invite our participants, if you do have questions for Dr. Francis, please, or comments, please put them in the chat box, and I will make sure that I pose those to her to field. I have another question here on the NOAA satellite images. We see there are a few altitudes that have wind moving in different directions. We mostly see clouds. Do these images show the jet stream? Is the jet stream at the highest altitudes compared to the others?
That's such a good question. And, most of my research for my career was using satellite data. So actually know quite a lot about this. Yes, there are clouds that do tell us something about the jet stream winds if they're the highest clouds. Once you get above the jet stream, you tend not to have clouds anymore. It's a very stable part of the atmosphere up where the stratosphere is. So those very highest clouds, which are also the coldest clouds, and that's how we can tell them apart, because there are certain satellite channels that show us temperatures, just like an infrared camera. things that are cold or warm show up differently in infrared wavelengths, so that we can look down, and when clouds are at different levels in the atmosphere, they are cold when they're high and they tend to be warm when they're low. And so those very high clouds, if there are any in a particular place, do tell us something about what the jet stream path looks like.
Thank you very much. I can totally see you in the classroom.
I don't do that anymore.
I have a feeling this is about the Supreme Court decision, and any insight about the EPA having less input in carbon emissions.
Yeah, I mean, it was a very disappointing thing.
Yeah.
It's not the end of the world, but right now what we need are more tools to help us address this crisis, not fewer tools. And so the Supreme Court just took away some of the EPA's tools to deal with this, to regulate emissions from power plants especially. So, they still have tools in their toolbox, but we, at this point in time, we don't have time. We're running out of time. We cannot lose tools. And those are important tools that they took away. So I found it very short-sighted, very politically motivated, and exactly 180 degrees from where we should be going.
And do you have any thoughts on the role of nuclear energy keeping us in the green line, that green line that you showed us?
Yep, I mean, that's a very controversial issue. I think nuclear electricity can be safe. In the United States, we basically stopped doing research for the most part. We stopped building power plants, nuclear power plants, decades ago. And other countries have plowed forward, and they have greatly improved the safety of nuclear electricity generation. And I think there's a lot of new technology that could be brought to bear to make a big dent in a type of renewable energy. I am a believer that we do need to include nuclear in the mix. It already plays a big role in many parts of our country, supplying electricity on a day in, day out basis. And I think, we can take advantage of the progress that's been made in the research world to make these plants much safer. But it's an uphill climb. People just don't want them in their backyards.
And then I have a question. Isn't the green energy hydrogen economy the only comprehensive solution, electricity and thermal, and that it's feasible using existing technology? If so, don't we roll up our sleeves and start building?
Hydrogen's complicated.
Yeah.
Right now it takes a lot of electricity to generate hydrogen. And the technology is still evolving. I mean, if we could partner solar with hydrogen generation or wind with hydrogen generation, that has the potential to decarbonize some of our transportation sector, which is a really hard one to decarbonize, especially when you start talking about airplanes and ships and things like that. So I think I think we're a ways away from having hydrogen play a big role, but there's certainly a lot of people working on that. There's a lot of really exciting research. So I think hopefully it will play a big role, but right now it's a long way from doing that.
There was also just something recently in the news. This isn't necessarily related. Well, it's related, but not directly to what you were just talking about, where they were talking about what is it? They're taking plants and they're creating plants that are going to be able to eat carbon faster. I don't know if you had seen anything about that or if you had any insight on that.
Well, one of the big directions that's going is with seaweed, and seaweed, and especially kelp, it sucks a lot of carbon out of the air and out of the ocean when it grows. And so there are a whole bunch of startup companies and organizations that are trying to figure out how to grow kelp at a massive scale in the ocean. And it has the benefit that you don't have to water it, you don't have to fertilize it, and it also creates its own ecosystem. It benefits not only this ability to extract carbon, but it also gives other animals a habitat. and it can be turned into a lot of amazing products as well. So not only when it grows does it sequester this carbon, but you can also use it to feed to cows so that they produce less methane. It could be made into a plastic substitute. It can be made into our food, into fibers that could be made into clothing. I mean, it's really quite an amazing plant. And so there's a lot going on in that direction.
And do you have, this is, I'm getting questions that are being sent directly to me. They are, do you have, for us, the people who are not in the thick of the research, do you have sites or resources that you would recommend that we can use to stay attuned of progress?
Oh, there are so many. I think there are a number of websites and climate communication groups that are doing a wonderful job. I think Climate Central is one of those. There are a number of books that have been written recently. In fact, Greta Thunberg has just written a new book called The Climate Book, and it's coming out this fall, and it's I actually contributed to it. And it basically takes the whole climate story from soup to nuts and explains it. It's a series of essays by over 100 scientists contributed to it, and it's extremely well done. The IPCC reports, the Intergovernmental Panel on Climate Change reports, are very dense, but there are a lot of sort of interpretations of those that you can find in various places online. Yeah, there's a lot of books out there that have been very well written. And books are static. That's the only problem with books. And so they do explain a lot of the science behind climate change and why, say, certain technologies have more promise than others and things like that. There's so many resources out there. I don't think they're hard to find anymore. There's a lot.
I just know that people get overwhelmed and they're looking for trustworthy, reliable information. I just know if you had a couple, if you had some that bubbled to the top. When I saw that question coming, I'm like, ooh, that's a doozy.
Yeah. So there's a good book written by a friend of mine named Bob Henson, who wrote a book called The Thinking Person's Guide to Climate Change. And that's also another really good one.
Okay. Thank you so much. There are a lot of other comments and questions, and for those that we were not able to get to, I just know that we're coming to the end of our hour, and I want to respect everybody's time. I can always talk to Dr. Francis about, and maybe pass these on to you to look and see, and I can address those that were not answered this evening. But I do want to thank everybody for the feedback, and just lots of kudos to you and thank yous for the presentation this evening. It really was very educational, and I appreciate it myself as well. So thank you so much.
Thank you everyone for being here and for caring.